Hey y'all, welcome back. So today in class we played a game on Kahoot where we answered a bunch of multiple choice questions, and I had a lot of requests for me to make a video going over all these problems because I know in class, I put you on the clock and you're very rushed through these problems and probably didn't get a lot of them either correct or really didn't finish working a lot of them. So all of these problems are good as far as helping to prepare you for both the midterm and the actual AP test later this year. So let's just go through these and make sure that you understand how each of these problems work. So the first one says if f is a function given by 4 over x plus 5x minus 1, then what is the instantaneous rate of change or the derivative of f at x equals 2? So this is what we're trying to evaluate. So first we need to find the derivative. And actually, before I even bother finding the derivative, I'm going to rewrite this first term as 4x to the negative 1, just to make it a little bit more obvious that we can use the power rule to differentiate. So using that power rule, especially on that first term, we're going to have negative 4 times x to the negative second power plus 5. Now we do need to evaluate this at 2, so you are going to have to know how to deal with that negative exponent. And I'll write that up over here. So f, I'm just going to rewrite what I just wrote there. I'm not going to make any changes yet. But yeah, so if I raise something to a negative power, that's equivalent to saying that it's 1 over the base to the positive power. So this would be negative 4 times 1 over 2 squared plus 5. So negative 4 times 1 over 4 would be negative 1. Plus 5 would be 4. So our answer is A. Number 2 says if f of x is e to the 2x times x cubed plus 1, determine the slope of the tangent line at x equals 2. Okay, this is basically the same thing as we had in question 1, where we're looking for f prime 2. Okay, that is what the slope of the tangent line to f of x at x equals 2 is. It's the instantaneous rate of change of f of x at x equals 2. So we're going to have to differentiate this and then substitute in 2 for x. So let's differentiate first. And to do that, we're going to have to use the product rule. So first, we'll find the derivative of e to the 2x, which is e to the 2x times 2 because of the chain rule, times the second function, which is x cubed plus 1, plus the first function, e to the 2x, times the derivative of the second one, which is 3x squared. So now to evaluate this at 2, I just want to substitute in 2 everywhere where I see x. So I have e to the 2 times, I'll do this in a different color just to make it a little bit more obvious, times 2. Well, we've got another times 2, but then now we're not in the exponent anymore. Times 2 times, too many 2's. 2 cubed plus 1 plus e to the 2 times 2 power times 3 times 2 squared. Oof, that's a lot of 2's. All right, so let's just be careful when we evaluate this. We get e to the 4th times, this is going to be 8 plus 1 is 9 times 2 is 18, plus e to the 4th again times, we have 4 times 3 is 12. So we've got a common factor here of e to the 4th. So f prime at 2 is going to be e to the 4th times the sum of 18 and 12. So f prime of 2 is going to be, let's see, 18 plus 12 is 30. So this is going to equal 30 times e to the 4th. So our answer, again, is A. Number 3 says let f be a function given by this rational function. For what values of x does f have an infinite discontinuity? All right, so to have an infinite discontinuity, our function must have a vertical asymptote. And this happens if you have a value that makes the denominator 0, but does not make the numerator 0. If you have a x value that makes both of those 0, Then you have a removable discontinuity or a hole. But for these infinite discontinuities, we need to find a value that makes the denominator 0 but not the top. So the easiest way to do this is to go ahead and factor both the numerator and the denominator. So we've got the denominator would be x plus 5 times x minus 3. And the numerator would be x plus 5 times 2x plus 3. Does that work? Let me just double check. We got 10 and 3. Yep, okay, so we're good there. So notice here that I do have a factor that's the same on the top and the bottom. Okay, this indicates a removable discontinuity, or a hole exists at -5. So this is a hole. This is a removable discontinuity. Okay, that's not what this question is asking for. It's asking for an infinite discontinuity, and that happens when we have an x value that makes the denominator 0 and not the top. So the only x value that's going to make the denominator 0 but not also the numerator is going to be x equals 3. And so our answer here is B. Number 4 says the graph of the function is of a function f is shown in the figure below. Which of the following statements is true? So first, we'll just go off and check these off. F of a equals 2. Well, here's a, and f of a is clearly not 2. F of a is 1. All right, I'll write down the true statement here. So it's not going to be a. It's definitely not going to be continuous at x equals a. You can see you have a hole that's a removable discontinuity, so it's not continuous there. C and D are talking about the limit as x approaches a. So you want to imagine that we are following this function from the left and from the right. And notice how both of these arrows are pointing to the same y value. That means that our limit is going to exist here, and it's going to equal 2. So it's not going to be 1, it'll be 2, and our answer is D. Number 5 says the limit as x approaches 6 of a function that's just 7. Whenever you have a constant function, like if you imagine this graphically, it's just going to be a horizontal line when when y is 7. And so if we're trying to find the limit as x approaches 6, let's say 6 is right here, the limit on the left and the right-hand side are both going to point towards 7. And hopefully you can see here that it really doesn't matter what x is approaching when you have a constant function. The limit is always just going to equal that function. So the answer is C. And that would be true if it was x approaches 1, x approaches 10, whatever. Number 6, the limit as x approaches 0. Okay, so we just recently learned about L'Hopital's rule, so I want to show you how you can find this limit using calculus. Okay, so to use calculus, we're going to use L'Hopital's rule. But I also, at least for this one, want to show you how to solve this using algebra. Okay, and we're going to use the factoring technique. And it's just kind of cool that you get the same answer in both cases. Now, we're only allowed to use L'Hopital's rule because if we try to plug in 0 here, if we use direct substitution, we're going to get a 0 over 0 situation. And that means we are allowed to use L'Hopital's rule. If we got anything else, if we got like 5 over 0 or 0 over 10 or anything like that, then we would not be allowed to use L'Hopital's rule. If you get infinity over infinity, that's fine too. Although usually it's easier in those cases to just plug in some large number and figure out what the limit at infinity is. So L'Hopital's rule says that this limit is going to equal the same limit of the quotient of the corresponding derivatives. So the derivative of the top is 3x squared plus 12x minus 3. Derivative of the bottom is just 1. So now if I go to plug in 0, I'm going to get 0 plus 0 minus 3, I get -3. So you can see our answer is A. But I also want to show you that this is a problem that we learned how to solve way before we learned about L'Hopital's rule. Back in the first unit, we learned how to solve this limit using factoring, since we had no idea what a derivative was at the time. So we can factor this. This is going to equal the limit as x approaches 0 of x times x squared plus 12x minus 3. That can't be factored anymore, I don't think. Yeah, I really don't think so. No, it definitely can't. And the bottom is just going to be x. Now we can remove the removable discontinuity and say that this equals the limit as x approaches 0 of x squared plus 12x minus 3 over 1 after reducing these x's to 1. And so look at that. Now I can plug in 0, no problem. I don't get any divide by 0 errors, and I still get -3. So you can solve this either way, whichever way you like better. I think L'Hopital is just like, a little bit easier than the factoring, but if you're really good at factoring, you might stick to the algebraic technique. Number 7 says, which of the following equations has a horizontal asymptote at y equals 5? So to have a horizontal asymptote, we need y prime to be 0. And so, unfortunately, it looks like we're just going to have to go through these one at a time and check to see if they have a horizontal asymptote at y equals 5. So let's find the derivatives here. Whoa. No, let's back up. Horizontal asymptote. No. Horizontal asymptote is going to exist when in order for it to be a y equals 5, the numerator, sorry, I misread that. I thought it was saying the horizontal tangent line. I don't know why I was thinking horizontal tangent line, but I was saying horizontal asymptote, and it says horizontal asymptote. So big difference there. So and for the horizontal asymptote to be y equals 5, the numerator's degree must equal the denominator's degree let's just move this over a little bit here. Okay, not only do the degrees have to be the same, but the ratio of the leading coefficient, ratio of the leading coefficients must be 5. So like 5 over 1 or something like that. This is actually going to be a lot easier. So we're just going to look at the sort of the biggest terms of both the numerator and the denominator. The square root of 25x squared is going to be the absolute value of 5x over x squared. In this case, the degrees are not the same. Right? The denominator is quadratic. Numerator would be linear. So yeah, this is going to have a horizontal asymptote of y equals 0. This is not going to be our answer. For part B, we've got 20x squared over 4x squared. And this one looks like we got some potential here. The degrees are the same, and 20 over 4 is 5. So it looks like our answer is going to be B. But let's just double check the rest. C, degrees aren't the same. This is going to have a horizontal asymptote of y equals 0. And for part D, the degrees are the same, but 5x over negative x, that ratio of the leading coefficients is going to be -5. So here are the asymptotes for each one of these. Just highlight these. Here's for A, here's for B, here's for C, here's for D. And the only one that has one at 5 is going to be B. Number 8 says, for what values of x does the graph have a point of inflection? So the point of inflection will occur whenever f double prime changes sign. So the strategy here is to find where f double prime is 0, construct a number line chart, and figure out where f double prime is positive or negative. So f prime is going to be 15x to the 4th plus 40x cubed. Y double prime will be, 15 times 4 is going to be 60, x cubed plus 120 x squared. If we set that equal to 0 to find our potential points of inflection, we could factor out a 60x squared and be left with x plus 2. So that's going to give us 2 subcritical values, one at 0 and one at -2. Now just a little hint here, since at this x equals 0, that factor has a multiplicity of 2, we should not expect a sign change there. So as you're doing this, if you get a sign change there, just double check and make sure you didn't make a mistake, either in your algebra initially or when you're plugging in the number. So here's my sign chart for f double prime, and we're looking for a potential sign change. So if there's a point of inflection, it's going to be at either -2 and 0. It might be both, right? If our answer is D, it could be both. But that would mean we need a sign change at both. Now, just as a little shortcut here, if you pay attention to the multiplicities, you can kind of get this question right without even doing the sign chart, because we know we've got an even multiplicity at 0. So I'm not expecting a sign change at 0. Our multiplicity of -2 is a root of y double prime. It has no multiplicity. It's just a single root. So we are expecting a sign change here. I don't know if it's going to be positive to negative or vice versa, but our answer is going to be -2 only. But let's just double check, make sure that our expectations meet the algebra. If I plug in a number like -5, I'm going to get a positive times a negative, which is negative. If I plug in -1, I'm going to get well, hang on here. If I plug in, did I plug that in incorrectly? -5 would be a positive times a negative is negative. Okay, so yeah, so if I plug in -1, I'm going to get a positive times a positive, which is positive. If I plug in 10, I'm going to get a positive. So yeah, we get exactly what we were expecting. No sign change at 0, and that's really due to that even multiplicity of that root of f double prime. And so our only point of inflection, oh, geez. Oh, there we go. Okay. Our only point of inflection is here at -2. Okay. The reason, like if it asks for a justification on a question like this, you want to say x equals -2, or you say there is a point of inflection at x equals -2 because the second derivative changes sign. That really is the justification there. Number 9 says, which of the following statements is true? And then it's comparing the values of f prime, and f double prime at these 3 points. So let's start with the first one. This could be a little challenging, like when you first look at it, because there's no numbers anywhere. So rather than thinking about numbers, what we want to be thinking about is, are these values positive, negative, or 0? So let's start with the first one. F of a. Well, a is below the x-axis. This really should be labeled as f. Okay, we're going to say that this is f of x. I'll have to remember to go back and label that, because otherwise you really can't answer this. So yeah, a is below the x-axis, so that means that f of a is negative. F double prime of b, okay, so double prime we're looking at concavity. Here we're concave up, so that means the second derivative is positive. And the slope at C, well, we can see that this has a horizontal tangent line, so the slope there should be 0. Okay, so A can't be our answer because we can't have positive numbers that are smaller than 0. Now, I think if I'm just glancing through this, it looks like those are the only, we don't have to recalculate anything. We have all of our pluses and minuses and zeros for everything we need here. So let's just make sure we get them in the right order here. Positive, 0, negative, that's not going to work. 0, negative, positive, nope. And then we've got f of a was negative, f prime of c was 0, and then f double prime of b is positive. So yeah, our answer is D. Number 10, the function f has a property that f is positive. That means that f is above the x-axis. Okay, where it also says that f prime is positive. Okay, so that means f has a positive slope. And f double prime is negative. So f is concave down. Okay, so we're looking for the graph that meets all 3 of these conditions. So let's look at graph A. It is above the x-axis. Okay, so we got our first check. We need 3 checks here. Has a positive slope, but it's not concave down. Okay, this is linear. So yeah, this is not concave down at all. Letter B, it's above the x-axis. Ooh, but it has a negative slope, and it's concave up. So yeah, this gets 2 x's. Definitely not going to be B. For part C, it's above the x-axis. It does have a positive slope, and it is concave down. So it looks like C is going to be our answer, but let's just double check D. This one is above the x-axis. It has a positive slope, but this one's concave up, so it's not going to meet the concavity requirement. So our answer is C. Number 11, find the derivative. So this is going to require a little chain rule and that you know your exponential derivatives. Go back and look at the notes that we did earlier today for a list of all the derivatives you need to know. And so I'm going to assume that you know this one already. So maybe I'll just write it to the side. The derivative of a to the x is a to the x times the natural log of a. So I just want to kind of remind you what that derivative is. Now we will have to use chain rule here because it's not just 11 to the x, but it's 11 to the x squared. So we'll have to multiply by the derivative of x squared, but otherwise it's going to be exactly just following this rule over here. So we've got y prime needs to be that 11 to the x squared times natural log of the base, which is 11, times the derivative of x squared, which is 2x. That's really all there is to it. The order here is different, but that's okay because multiplication is commutative, which means that the order doesn't matter. In other words, like 2 times 3 is the same as 3 times 2. So this says 2x times natural log of 11. I wrote natural log of 11 times 2x. It doesn't really matter which way it goes. Number 12, find the derivative. Okay, so there's going to be a logarithmic derivative. And so as a little reminder here, like I reminded you up here, the derivative of log base a of x is going to be 1 over x times the natural log of a. And of course, just like with the last one, we're going to have to do a little chain rule too. So let's find y prime. So it's going to be 1 over x times the natural, not x, sorry, because it's not just x inside the parentheses, it's 6x plus 5, times the natural log of 4, times the derivative of 6x plus 5. So that's times 6. Now, none of the answer choices look exactly like that, so let's just try to simplify a little bit. 6 times 1 is 6, and I think that's all we're going to have to do, and I don't even really think there's anything more we could do. Let's look. 6 over, yes, our answer here is C. Number 13, we're looking for the derivative, and so this is just going to require that you know your derivative rules for natural log. It's very similar to log. It's actually a little easier because the natural log of v is 1. So yeah, y prime or dy dx, right? That really is y prime. Both of those two things mean the same thing. It's going to be 3 times 1 over x squared minus 3 times the derivative of x squared minus 3, which is 2x. So we can simplify this. 3 times 1 times 2x will be 6x over x squared minus 3, and that's it. So do we have that one? Yep, that's going to be answer choice A. Always a little satisfying when you see your answer in the answer choices. Not to say that that for sure means it's right, because a lot of times these answer choices are designed to look right if you make a mistake, like they've been kind of worked out incorrectly in several ways. So it's possible that you see your answer when you get it wrong, but most of the time, if you're feeling confident about the problem and you're doing everything the way you're supposed to be doing, if you see that answer choice, that can be pretty reassuring that you got it right. So anyway, number 14, we're finding another derivative. Another kind of basic derivative problem. Dy dx, which is the same thing as y prime, is going to equal 3 plus the derivative of log base 3 of x. This is just a basic logarithm derivative. So we got 3 plus 1 over x times the natural log of 3. And yeah, our answer is A. Not much to say about that one. 15. Now here we're getting into implicit differentiation. So here we're going to have to differentiate both sides of the equation and then solve for dy dx. Now, just for the sake of cleaning up the notation and everything, I'm going to use y prime instead of dy dx. I just think as you're going through this, writing the dy dx gets a little tedious, a little annoying. I'm not saying you can't write it, but I'm going to choose to go with y prime as I work through this problem. So the derivative of the left-hand side will be y prime. And then we got to use product rule here. Now be careful. I'm going to put parentheses here, but normally when I work this, I'm going to just make both terms negative. But you'll see what I mean in a second. The derivative of 2x is just 2, derivative and then times y, plus 2x times the derivative of y. And then that's going to equal the derivative of 3x is 3. Now, when I distribute that negative sign, I'm going to get minus 2y minus 2x y prime. What I was talking about earlier is usually I'll just jump straight to this step. If I see that minus, I know that both of these terms are going to end up being negative. If you want to be safer, put the parentheses there and do it as a separate step. But hopefully, you get to a point where you've done enough of these product rule problems where it's negative and then a product rule that you just are ready to expect both of those terms to be the opposite of a positive. So now we need to solve for y prime. So I'm going to keep my terms that have y prime on the left-hand side and factor the y prime out as a GCF. So I'll have y prime times 1 minus 2x, and then I'll bring that extra negative 2y. I'm going to add 2y to both sides to get 3 plus 2y. So just kind of rearranging a little bit there. And then I want to divide both sides by 1 minus 2x. So I get 3 plus 2y over 1 minus 2x. Where is our answer here? It looks like it's right here. Oh, it's A. I read over it the first time. Yep, there you go. Number 16, find the slope of the line tangent at 2, 3. So what we need to do is find the slope. We need to find that y prime, or that dy dx. So we're going to have to use implicit differentiation, and then we'll substitute in 2 as x and 3 as y. So the derivative of x cubed is 3x squared. You're going to have to use product rule here, but no tricky negatives, so we can just kind of go forward. Business as usual here. Actually, the derivative of 2x is just 2. So 2 times y plus 2x times y prime minus y squared. Oh, not minus y squared. We need to differentiate that. Sorry. 2y times y prime equals 0. The derivative of any constant is going to be 0. Now, just like the last problem, I want to isolate the y prime. So I'm going to factor out that y prime out of the two terms that have a y prime. These two right here, leaving me with 2x minus 2y. And then I'm going to move the terms that don't have y prime over to the right-hand side. So I'll have negative 2y minus 3x squared. Those terms you can write in either order. Doesn't really matter, but I chose to put them like that. So now I'll divide both sides by 2x minus 2y. Get negative 2y minus 3x squared over 2x minus 2y. So this is our formula for the slope at any point. But now we want to evaluate this at 2, 3. So I'm going to substitute in 2 for x and 3 for y. So y prime at 2, 3 equals, let's just go through it, negative 2 times y, which is 3. So I'm going to say times 3 minus 3 times x squared. So that would be times 4 because x is 2. Divided by 2 times x, which is 2, minus 2 times y, which is 3. So this would be negative 6 minus 12 over, what was that? 4 minus 6. So that'd be negative 18 over negative 2, which equals positive 9. Yeah, that took a way more room than I gave you on that one. Sorry, that kind of bled into our space on 17, but that's okay. We'll make it work. Number 17, we're looking for the derivative. Okay, again, we're just looking for that dy dx, or that y prime. And so this is going to be very similar to the last few problems. The derivative of x squared is 2x. The derivative of x times y, we're just going to use product rule here. Derivative of x is 1 times y plus x times the derivative of y plus 3y squared, then due to the chain rule, times y prime. Now I'm going to isolate y prime. I'm going to factor it out of the two terms that have a y prime. So that's going to leave me with x plus 3y squared. And then I'm going to move the 2x and the y over to the right-hand side. Now I've got y prime equals negative 2x minus y over x plus 3y squared. Okay, now just want to be a little careful when you're looking through these answer choices because none of them look exactly like this. But if you look at choice C, which is going to be our answer here, this negative would get distributed to both of these, and we see we have both negatives there. So everything is accounted for. Number 18, we've got some position, velocity, and acceleration going here. Just as a little quick note here, the derivative of the position is the velocity. Let's make sure we write that statement. Additionally, the second derivative of the position, which is the first derivative of the velocity, is acceleration. So let's make sure we understand the relationship there between position, velocity, and acceleration. And just writing that down, these two statements, every time that you have a PVA problem, position, velocity, acceleration problem, will, I think, really help kind of guide your process on solving any of these. So anyway, we're trying to find the value for t for which the acceleration is equal to 0. Okay, so first we have to find the acceleration. They give us p here. Let's start by finding v. And we said before that velocity is the derivative of the position. So that would be negative 6t squared plus 18 times 2, 36t plus 8. And our acceleration, which is the derivative of velocity, or we could say the second derivative of position, would be negative 12t plus 36. Okay, so that's our formula for acceleration. We want to find when is the acceleration equal to 0. So we'll just set this acceleration equation equal to 0, subtract 36 from both sides, and divide both sides by negative 12. We're going to get t equals 3. Our answer is D. Number 19, we're given a bunch of values for f and for f prime. Oh, and okay, so we're going to find the derivative of, the derivative of the inverse of f, where f, with this negative 1. Basically, this is just spelling out that there is a little bit of ambiguity if you don't say this, where if you say f negative 1 here, it's not super clear if this is like f raised to the negative first power versus the inverse of f. So the A/B test will be pretty explicit about like stating when it's supposed to be the inverse. And most of the time, it's almost, I don't want to say it's safe to assume that it's talking about the inverse, but very rarely are you going to get something like this and it means like 1 over f, which would be the reciprocal. Okay, so we want to find the derivative at x equals negative 2. So we have the inverse. I'm going to, actually, you know what I'm going to do? I'm going to say let g be the inverse of f, just to make the notation a little nicer here. So what we're looking for is the derivative of that inverse at x equals 2. Oh, not x equals 2. X equals negative 2. So this is going to be 1 over the derivative of f at g of negative 2. Okay, so this is really what we're trying to evaluate here. So a couple little points here. Since g is the inverse of f, that means that when we have a point 4 comma negative 2 on f, we're guaranteed a point g of negative 2 equals 4. So negative 2 comma 4 would be on the inverse. Similarly, with this second statement here, we can say that g of 3 is negative 2. So g of negative 2 is 4. So this is going to equal 1 over f prime at 4. And that is given. F prime of 4 is 5. So this is going to be 1/5. Number 20 says let f of x be x cubed plus 3x minus 8, where f of 2 is 6. Find the derivative of the inverse. Another inverse derivative problem. This time I won't do the whole let g of x equals f inverse. I want to show you kind of just what's going on behind the scenes there. So here's, I didn't write it before, but if you have an inverse, right, and you want to find the derivative of that inverse, that's going to be 1 over the derivative of the original function, not the inverse function, of the inverse of x. Okay, this is our derivative rule that we're going to be working with. So let's so if we want to find the derivative of f of the inverse of f, so here's the inverse of f. We want to find the derivative of that when x equals 6. So I'm going to plug in a little 6 here. That's going to equal 1 over f prime of f inverse at 6. Now, because we know that f of 2 is 6, we know f inverse of 6 is 2. So this f inverse of 6 is 2. So we have 1 over f prime of 2. Now we do need to find f prime to be able to finish answering this question. Here's f. So let me make sure we know that this is part of that. I don't want to get these mixed up. So yeah, let's find the derivative of f here. I'll work that out, I guess, down here. The derivative of f is 3x squared plus 3. So if I want f prime of 2, that's going to be 3 times 4. 12 plus 3 is 15. So this is going to equal the derivative of the inverse of f when x equals 6 is going to be 1 over 15. Our answer is A. Number 21 says, given that the derivative of y with respect to x is this expression here, and we've got a coordinate 3 comma negative 2 on f, use the tangent line at x equals 3 to approximate f of 2.9. So first we need to find the slope when x is 3. So anytime you're trying to use a tangent line for approximation, we're going to write that tangent line the same way we write all of our tangent lines, which is to say we're going to identify the point of tangency, we're going to find the slope at that point, and then we're going to write our equation in this point-slope form. So that point of tangency is given right here. They say at x equals 3, and most of the time you have to actually go and find y, but because the original function f is not given, they do have to tell us what the y value is there to be able to solve this. So the y value of the point of tangency is going to be negative 2. The slope at that point of tangency is going to be the value of dy dx at 3 comma negative 2. So we're going to substitute in 3 and negative 2 into x and to y. So this will be negative 2 cubed times 3 over 3 times negative 2 plus 2. So that'll be, let's see, negative 2 cubed is going to be negative 8 times 3 over negative 6 plus 2 is going to be negative 24 over negative 4. So that's going to be 6. Unless I made a mistake somewhere in there. So my slope is going to be 6, and now I've got my equation. Y plus 2 equals 6 times x minus 3. Now I'm going to use that equation to approximate f of 2.9. So basically what I'm going to do here is I'm going to plug in 2.9 into x. Y plus 2 equals 6 times 2.9 minus 3. And then I'm going to solve for y. So 2.9 minus 3 is negative 0.1. Y plus 2 equals 6 times negative 0.1. Negative 0.1 times 6 is going to be negative 0.6. And then if I subtract 2, I'm going to get negative 2.6. So our answer is D. And what this means is that, if we have some curve here, I don't really know what's going on with the curve, but with our tangent line, this represents the point on the tangent line rather than the actual curve. It is an approximation. We don't have enough information to find out the exact value, so I can't sketch a picture or anything for you here at this point. But yeah, the approximate value of f of 2.9 is going to be negative 2.6. Number 22 says the position of a particle. Okay, another PVA problem here. So remember, acceleration is the derivative of velocity, which is the second derivative of position. And if we're talking about velocity here, velocity is the derivative of position. I really like just stating that up front to make sure you can get those points. Anyway, it's given by this little formula here. So we are going to need our arctangent derivative, and then we will determine the velocity at t equals 3. So basically, we need to find the velocity function, which is the derivative. Oh, in this case, we're not going to say p, we're going to say x. Okay, the position is given by x, so x of t, or the derivative of x of t, I should say. Now, the derivative of arctangent is going to be 1 over 1 plus x squared, but I don't have just x. I've got 2t plus 1. So it'll be 1 over 1 plus 2t plus 1 squared. And then using the chain rule, I'm going to have to multiply by the derivative of 2t plus 1, which is just 2. And just to simplify things a bit, I'll do the 1 times 2. and put that 2 in the numerator. So now I just need to evaluate this when t is 3. So I'm going to find v of 3. This is 2 over 1 plus, let's see, 2 times 3 is 6, plus 1 is 7, and 7 squared is 49. So this is going to be 2 over 50, or 1 over 25. Our answer is C. Number 23, if g is the inverse of f, use the table to find g prime of 3. Okay, well, if we know g is the inverse of x, then we know how to find g prime of x. That's going to be 1 over f prime of g of x. And so if we're trying to find g prime of 3, that's going to be 1 over f prime of g of 3. Now, g is not in this table, but we do have f, and g is the inverse of f, so it might be worth just taking a second here and creating a table of values for g. So all you have to do is just reverse the x's and the y's here. So we've got a point 9 comma negative 5, 6 comma negative 4, 4, 0, 2, 3, 3, 7, and negative 5, 8. These are all coordinates on g. So what we're interested in here, though, is g of 3, which is 7. So this value is going to be 1 over f prime of 7, and f prime of 7 is going to be negative 5. So we get 1 over negative 5. Our answer is A. Number 24. Tangent line was used to make a function approximation for f of x. Given that f prime is positive, okay, so f prime being positive means f has a positive slope, or f is increasing. Okay, and f double prime is negative. That means f is concave down. Is the approximation greater than or less than the actual value of f of x? So since we know it's concave down, the fact that f is increasing, not as big of a deal. But because it's concave down, we're going to have a curve that basically does something like this. Okay, the point of tangency where f is increasing is going to be like over here. It wouldn't be over here because f is decreasing over there. So like somewhere right there. And so if I use this tangent line as an approximation for the values that are on the function, you can see that that tangent line is above the curve. So this is going to be an over approximation. This is the approximation is going to be greater, and the reason is not because the f is increasing, because the line would be above over here as well, so it really has nothing to do with the fact that f is increasing. It's because f is concave down, and that is due to the fact that the second derivative is negative. So our answer is C, that our approximation is greater than the actual value because the second derivative is negative. Number 25, we've got an equation with x and y. It says use the equation of the tangent line at x equals 1 to approximate the value of y when x is 1.2. So another tangent line approximation problem. So we need to come up with that tangent line. We need the point of tangency, and that point is going to be 1 comma something, although we'll have to find the something at this time. The slope will be the slope at the point of tangency, so we'll have to find y prime. Then we're going to write our equation in point slope form. And then finally, we're going to plug in 1.2 into x. So let's go back, and we need to find first the point. So we need to plug in 1 into the original equation. 1 cubed plus 2 times 1 squared times y minus 4y equals 7. And we're going to solve for y. 1 cubed is 1 plus 2y minus 4y equals 7. 2y minus 4y is negative 2y. 7 minus 1 is 6. And 6 divided by negative 2 is negative 3. So the y-coordinate of the point of tangency is going to be negative 3. The slope will be based on the derivative here, so this is going to take a little bit extra work. Let's see here. The derivative of our equation will be 3x squared plus, we're going to have to use a product rule here. So the derivative of 2x squared is going to be 4x and then times y plus 2x squared times y prime minus 4y prime equals 0. I'm trying to solve for y prime so that I can get the slope for my tangent line approximation. Y prime, if I factor that out of these two terms, will leave me with 2x squared minus 4. and then subtracting the two terms that don't have the y prime over to the other side. That'd be negative 4xy minus 3x squared. So y prime is going to be negative 4xy minus 3x squared. Oh, that is an ugly 2. That does not look like a 2 at all. Over 2x squared minus 4. Okay, whew, that took a lot of algebra. So now we can find the slope at 1 comma 3, or 1 comma negative 3. So we have negative 4 times 1 times negative 3 minus 3 times 1 squared over 2 times 1 squared minus 4. Let's see if we can simplify that. Negative 4 times negative 3 is going to be 12. Negative 3 times 1 is negative 3. 2 minus 4 is negative 2. So we get, oh, is this going to be a fraction? Oh, come on. Yeah, we get negative 9 halves. Ugh. Or negative 4.5, whatever's easier for you. But there we go. Okay, so negative 9 halves would be our slope. You know what, I'm going to move this little section a little bit further down here. Just to give me a little bit more space to create my equation. All right, so let's write our equation. Y plus 3 equals negative 9 halves times x minus 1. And we're going to substitute in 1.2 to get our approximate value. Really hope I didn't make a mistake somewhere in here. There's a lot of room for error. So if I do, we'll always go back and we'll fix it. But fingers crossed. We got y plus 3 equals negative 9 halves times 1.2 minus 1. 1.2 minus 1 is going to be 0.2. So we have 0.2. Maybe I'll turn this back into a fraction. It might be easier to do the arithmetic here. So 2 tenths is 1/5. Okay, 9 times 1 is 9. 2 times 5 is 10. So we get y plus 3 equals negative 9 tenths. This is 0.9. So now, yeah, I'm actually going to go back to decimals here. Y plus 3 equals negative 0.9. Then I could subtract 3. So I'm going to get negative 3.9. Is that an answer choice? Please let us say it. Yes, it is. Oh my gosh. I was really worried about this one. I was pretty sure I was going to get that one wrong. There's just so many opportunities for error here. Wow. I'm ready to be done with that one for sure. That is a beast of a problem. Keep that in mind for next year. Maybe give you more than 60 seconds to do that problem. Yeah. All right. Number 26. All right, this looks like a limit problem, but it's actually a derivative problem in disguise. This is the limit definition of the derivative. So really all we have to do here is differentiate this function right here. So this whole limit is just simply going to equal the derivative of arc cosine of 2x. So this is going to be one of those newer derivatives that we've just recently learned. Hopefully you've got it memorized. If not, just keep working with it and you'll get it. It's going to be negative 1 over the square root of 1 minus the quantity squared, in this case 2x squared. Using the chain rule, we're going to have to multiply by 2. So I'm actually going to rewrite this negative 1 as a negative 2 because negative 1 times 2 is negative 2, and I'll just make things a little bit simpler. Yeah, that's it. So let's see if we got it somewhere in there. The only other thing I guess we could do is square the 2x, and we would get the square root of 1 minus 4x squared, which is the format that we see the answer in. It's going to be A. Number 27, another limit problem. Okay, so here we have something a little bit different going on. If I try to use direct substitution here, I'm going to get 0 and then over 0. So that's a problem. Now don't write equals 0 over 0. Nothing can equal something that's undefined. You will get points taken off if you ever write equals 0, 0. Basically, I want you kind of allergic to writing 0 over 0. Like, just never write that, and then you will never get points off for it. You do have to check, though. It's sort of like a weird little thing here where you have to check and make sure that you can actually use L'Hopital's rule, but that is what we're going to do. We're going to use L'Hopital's rule on this one. So it'll equal the limit as x approaches -2 of the derivative of the numerator divided by the derivative of the denominator. The derivative of the numerator is simply 1. The denominator is going to be 1 over x plus 3 times the derivative of x plus 3, which is just 1, so I can kind of ignore that. Now I've got 1 divided by a fraction. I'm going to simplify that. Whenever you're dividing by a fraction, that's the same thing as multiplying by the reciprocal, so this is just going to turn out to be x plus 3. And then if I substitute in -2, I'm going to get -2 plus 3, which is +1. So our answer is C. One quick note here, I still have a lot of students struggling with like when to stop writing the limit notation. And it's this step right here. It's when you plug in. So when you substitute, stop writing limit, okay? Whenever you plug the number in, that is when you are evaluating the limit. So you do not need that limit notation any longer. Number 28. Let's try to find this limit. Looks like it's probably going to be another L'Hopital problem, but let's just double check. Plugging in 1 at the bottom gives me 0. Plugging in 1 at the top, sine of pi is also 0. So I don't want to say this thing equals 0 over 0, but I know that that's what I'm going to end up with if I use differentiate the top and the bottom. So I'm just going to go ahead and use L'Hopital's rule here. So this is going to equal the limit as x approaches 1 of the derivative of the numerator. Derivative of sine is cosine, so cosine of pi x times the derivative of pi x, which is just pi. Pi is just a constant here, and like if it was cosine of 2x, it'd be cosine 2x times 2, divided by the derivative of the denominator, which is just 1. So now I shouldn't have any problems using direct substitution here. So actually, I'm not even going to write the limit because I'm going to go ahead and directly substitute. Cosine of pi times pi. Now cosine of pi is -1, so we have -1 times pi, which is negative pi. Our answer for 28 is D. Number 29, what's the value of this function approach as x approaches 0? So in other words, this is saying, what's the value of the limit as x approaches 0 of e to the 5x minus 1 over 3x? And it won't take long for you to realize that if you substitute 0 in here, you're going to get a 0 over 0. So we're going to have to use L'Hopital's rule. So this will equal the limit as x approaches 0 of e to the 5x times 5 to the chain rule, divided by the derivative of 3x, which is 3. And now we can plug in 0. E to the 0th power is 1, so we just end up with 5/3. Number 30, we're trying to find another limit, and it looks like this is just going to be another case of L'Hopital's rule, because we get 0 over 0 when we try to use direct substitution. So I'm just going to move this, give myself a little bit more room over here. So this is going to equal the limit as x approaches 0 of the derivative of the numerator divided by the derivative of the denominator. Now, the derivative of x is just 1, so I'm going to do the easy one first. We are going to have to use product rule for the numerator. The derivative of sine is cosine, so I get cosine times cosine. And then I have plus sine times the derivative of cosine, which is negative sine x. So just to combine these a little bit, I'm going to get cosine squared x minus sine squared x. Now I can go ahead and plug in the 0. Cosine of 0 is 1, so I have 1 squared minus sine of 0 is 0, so that's 0 squared. So this is just going to be 1. Our answer is C. Number 31, what's the horizontal asymptote? Okay, this is, I think, the second horizontal asymptote question we've seen. When you have a rational function, the horizontal asymptote will be the limit as x approaches infinity, or negative infinity. I guess I should say plus or minus infinity if we're going to be inclusive here. And so when you have a rational function and it's just a polynomial divided by another polynomial, you really just want to look at the leading terms. So basically what we want to find is the limit as x approaches infinity of x cubed over negative x to the fourth. And if your denominator is growing faster than the numerator, no matter what else is going on, this thing is just going to be 0. So we've got a horizontal asymptote that is 0. Number 32. Now, be careful on number 32. We want to approach it kind of the same way we did 31, but when you have that square root of a square, we want to take great care in rewriting this. So I'm just to look at my biggest terms on either side. So I've got x over, and I've got this square root of 4x squared. Now, be careful. You're going to be tempted to write 2x. But the square root of a square is actually the absolute value of that square root. So this is actually the absolute value of 2x, which means that if x is going to infinity, this is going to go to, well, 1/2. But if x was going to negative infinity, because of that absolute value, this would go to negative 1/2. Oops, I didn't write the negative for some reason. So just be careful with the whole square root of a square deal, where you typically are going to get 2 horizontal asymptotes on these problems, and the limit as x goes to plus or minus infinity is going to be different. That doesn't happen really on any of the other problems we've seen so far. This is really the only case. I mean, there are other functions that have multiple horizontal asymptotes. Well, I guess you can't have more than 2, but this is really the only one I think you're going to be faced with. So just be very careful. Now, this one, you really can't go wrong because it says x goes to infinity. So even if you didn't catch that, you're still going to get this one right. The answer is C. Number 33 gives us a piecewise function, and we want to determine if, first of all, the limit, or if there is a limit at x equals 2, is it continuous at x equals 2, and is it differentiable at x equals 2? So let's double check. So what we want to see is what is going on here. Okay, so x squared minus 4 is the same thing as x plus 2 times x minus 2. All right, so this tells me that I have a hole at x equals 2. In other words, what's happening is I have this straight line with a y-intercept of 2, slope of 1, and I've got a hole at x equals 2. So I've got a little hole here. Okay. Now, when x is 2, the value of the function is 1. So that's going to be like down here. Now, you don't have to necessarily graph this out. You could just plug in the numbers and see what happens. But I think drawing the picture can really be helpful to see what the answer is going to be. We can see for sure that there is a limit at x equals 2. Okay, even though we have a removable discontinuity or a hole here, the limit is still going to exist. However, because we do have that removable discontinuity, it is not continuous. Okay, and if a function is not continuous, it can't be differentiable. Okay, so if it's differentiable, it will for sure be continuous. Okay, differentiability implies continuity. Not the other way around, though. It could be continuous and not differentiable. For example, if you have the absolute value function that has a sharp turn, that's continuous but not differentiable. So if something's differentiable, then it's for sure continuous. But we can also say the contrapositive is true too. If it's not continuous, then it's not differentiable. So the answer here is A. Okay, last page here. A lot of good problems. Okay, these all, if you really don't, there's enough problems on the actual midterm review, I think that you can use to study. You don't really have to go through all these, but it doesn't hurt to just listen to a few extra problems, just so you know for yourself whether or not you understand the key concepts from this semester. Okay, let's see here. We've got a piecewise function. C and D are constants. It's differentiable at 2. So remember, differentiability implies continuity. So because it's differentiable at 2, it also has to be continuous at 2. And we want to know what is the value of C plus D. So we need to find both C and D. What we're going to do is we're going to set up 2 equations. One that we'll get from the fact that the function is continuous at x equals 2, and one equation from the fact that it's differentiable there. So because the function is continuous at x equals 2, that means these two pieces must be equal at x equals 2. So 2c plus d has got to be equal to 4 minus 2c. So basically I just plugged in 2 to all the x's and set these equal to each other. Now, if I solve this for d, and really you can kind of manipulate this any way you want, but I notice that d is kind of all by itself. Its coefficient is 1, and so it'll be easy to solve for. I'm going to solve for d. So I have d equals 4 minus 4c. Okay, so that's one equation that we have. Now let's come up with an equation based on the fact that we want this to be differentiable at x equals 2. And so we'll have a very similar setup here, but instead of setting the actual equations equal to each other, we're going to set the derivatives of those pieces equal to each other and still plug in 2 for x. So I'll do the plug in 2 separately here. I did it here just right away because I think you guys could see that pretty easily, but sometimes the derivative, I don't want to do too much at once. But the derivative of the first piece is just c. The derivative of the second piece is 2x minus c. So if I plug in 2 for x, 2 times 2 is 4. So if c equals 4 minus c, and I add c to both sides, I get 2c equals 4. Divide both sides by 2, I get c equals 2. And once I have c, I can plug that into my d equation. So d is 4 minus 4 times 2. That's 4 minus 8. So d is negative 4. Okay, the question's asking for c plus d. So 2 plus negative 4. So c plus d is 2 plus negative 4. That's negative 2. Our answer is B. Number 35 says the graph of a function f is shown. At which value of x is f continuous but not differentiable? Okay, so again, remember, just because something's continuous, that doesn't necessarily mean it's differentiable. So the places where it's not differentiable is where you have either like a discontinuity, first of all, or you have a vertical tangent line. This one's kind of just off the top of my head here. Or if you have a sharp turn. Okay, this is kind of what you're looking for. And really the only thing that, if we look at A, we do have a sharp turn, so it's definitely not going to be differentiable there. So that's going to be our answer. Just cut straight to the chase here. B, we do have a discontinuity, so it's not continuous at B. D, we've got a discontinuity, so it's not going to be continuous. And I guess that's all we had to check. Oh, C. C is continuous, but it's also differentiable. So we don't have a discontinuity, a vertical tangent, or sharp turn there. So yeah, our answer here is going to be A. Number 36, which of the following statements about the function f of x equals absolute value of x are true? And to help us out, we're going to draw absolute value of x here. So this V-looking graph. Okay, letter one, number one. Although it is a letter, I. Okay. Anyway, it is continuous at x equals 0 for sure. But it is not differentiable there. We have a sharp turn, so it cannot be differentiable there. And it is an absolute minimum. Okay. It's also a local minimum, a relative minimum, but because this is the absolute lowest point on the graph, it's also considered the absolute minimum. So our answer here will be C. That brings us to our very last problem of this very long worksheet here, 37 multiple choice items. Hopefully you had a little bit more fun doing them with the game than just like working them out, one at a time. That can get kind of boring, honestly, unless you're just really into this like me. But yeah, let's knock this out. Let's send this one home. 37 says a graph of a function f is shown in the figure. Or the graph of the function f shown in the figure has a vertical tangent at 2, 0. So we got a vertical tangent right here, and horizontal tangents at 1, -1. So horizontal tangent here, and 3, 1. For what values of x on the interval is f not differentiable? Okay, so we went through like the different reasons why a function might not be differentiable. So we're looking for any instances of those. So first, let's look for the discontinuities. And there's only one discontinuity here, and that's at 0. So it's definitely not going to be differentiable at 0. So I'm going to highlight those. Okay, so we definitely got 0. And so we can eliminate C. And then we want to look, and so another reason why a function might not be differentiable is if you have a vertical tangent line. So that's going to happen at x equals 2. I got a vertical tangent line here. So we need to make sure we're accounting for 2. And so, yeah, we can get rid of choice A now. And so now we just need to narrow down between B and D. And the only difference here is that D includes 1 and 3. Now, at 1 and 3, we have horizontal tangent lines. But that's okay. That does not prevent the function from being not differentiable. So our answer to number 37 is B. And that wraps it up for these 37 multiple choice problems. I hope you understand the ones you were struggling with a little bit better, but as always, please reach out if you have any questions or want me to clarify any of these problems, go into a little bit more detail. I'd be happy to do that for you guys. But yeah, thanks for watching. Y'all have a great day.